So I will speak about what we have done in the diagnosis chair. So it's a chair that is dealing with model-based and database diagnosis. So here are the people of the chair. So Xavier from Onera, Elodie from LAS, from my team in LAS, and Nathalie Barbosa was with us at the start, more than 2 years. She was here, and she was with Vitesco Technologies, and then she launched her own activity. And then, of course, some colleagues of the DISCO team in LAS. So the topics that we have been covering in this chair is anomaly detection. You saw many of the works we have done presented by Christophe Merle, and diagnosis, because these two topics are closely related. Anomaly detection can raise some symptoms that when they are analyzed can lead to a root cause, which is a diagnosis. So anomaly detection is not only seen as a way to certify data quality for example, neural nets, but also as a way to write some symptoms when we want to produce a diagnosis. And these two tasks are closely involved for predictive maintenance and for monitoring and surveillance of the plants. Okay, in this framework, we have been working towards extracting knowledge from data and integrating knowledge and data to make better systems. Okay, so this is a view of the position of the chair in the different teams of ANITI, and we have been core to the team data and anomalies, of course, but also related to the team explainability, automatic reasoning, and decision making. So what have we done? I will start by what we have done apart from pure science. And here are some popularization events. In particular, we have been closely involved in the creation of an escape game that is called Je peux IA. And the weekend is coming, so you can have your children go and play, like you see here, Marjorie trying to figure out one of the problems that are in this escape game. Then we have organized some events, in particular the workshop on principles of diagnosis that was shared by Elodie and Pauline. And from the teaching point of view, none of the chairs has spoken about this, but I know that it is important in ANITI. So we have been doing things on this. One of our students was doing AI sessions at INSA. There has been the creation of 2 new lectures by Elodie Chantery, and myself, every year I have a recurrent lecture on diagnosis and supervision at ENAC. So from the scientific outcomes, the 4 items that are here are the items in which we have contributed. So first, implicit knowledge extraction from process data flows. So this is some work that Christophe mentioned and that produced some quality indicator for products of a production chain. And also, we were using some GNN to be able to predict the remaining cycle time of products. Then we have been, of course, producing new methods for anomaly detection. In particular, the method that was presented by Charlotte for irregularly sampled and distorted time series, but also the method based on Christopher function that we we were contributing with the polynomial optimization chair on this work that we would like to continue. And then some methods based on dynamic clustering for frugal embedded anomaly detection. The third topic is about building architectures that include some machine learning tools for fault and performance loss diagnosis. In this work, knowledge and data are present, but they are used at different steps of the process. And in the fourth item, that's where we integrate more closely knowledge and data, and this is what I will present a little bit in more deeper details further on. So here are the PhD theses. 6 of them have already been defended, and we still have 2 theses going on, Charlotte and Louis Goupil. So Charlotte presented her work, and I will present a little bit the work of Louis. That he's working on this tree-based diagnosis with some meta-knowledge about diagnosis. And this is the team who supervised all these students. So these students were all working in collaboration with some industry. So you can see here Vitesco, CNES, Atos, Fiji, Carl Berger-Levrault, and again, a lot of Vitesco projects. And this has led to 3 patents that are pending. One by Fiji that was already mentioned on this problem of diagnosis faults on photovoltaic panels, and 2 on the work with Atos. So a bit of what is going on now, and I will present what what is going on in the thesis of Louis. So first, I want to remind a concept that comes from model-based diagnosis. When we have a system, this system has an internal state, X. Generally, this internal state is not measurable. We don't have measures and sensors for this. And then this system can be impacted by faults. But then we have the inputs and the outputs that are measured generally, and so we have some observations. This produces the observations. So when we want to monitor such a system, what we need are some diagnosis tests, and these tests must be produced from the measurements that we have on the system. So generally, when we have a model, this model can be of different forms, but it's a mathematical model. If we succeed in eliminating the unknown variables X, we can deduce from the model some relations that depend only on the observable variables. And these relations, they are such that when they are satisfied, so here what is called the residual is 0, then the observations are consistent with the normal behavior of the system that is represented by the model. So that is some knowledge that we will use and we will integrate now, and I will show you how. And to do this and to be simple, I will use this little system that is a simple static polybox in which the boxes are multipliers and adders. And it has this structure where the intermediate variables T, U, W are unknown, and we have the knowledge of the inputs here and of the outputs. For this very simple system, if you eliminate the variables by doing some substitutions, you get to these 3 relations, and these relations, they are each sensitive to a subset of faults. And these relations can be checked from the values that we get for the observable variables, and you can figure out from this matrix which is the fault that the system is suffering. So the problem now is that we don't have a model. There are many cases, in particular for complex systems, in which we don't have the model. So what we can do is use the data from the system. And an idea that has been used very commonly is to use decision trees. And thank you to Joa. Now you know what are decision trees. And so here you have what you can do. You can have all the data of the nominal case and of the different faults of your system, and the decision tree can be built so that at the leaves what you want is to have the different faults that are indicated. Okay, but this, we tried the normal, the standard decision trees univariate, and it didn't work so well. So actually the idea and the intuition we had is to use the knowledge we have from the model-based diagnosis and try to do something with this. And so we decided to inject the knowledge of the properties of these relations and to branch on finding the relations that are given intuitively from the knowledge we have when we work with model-based diagnosis. But to find a relation, to discover a relation, then we have to rely on symbolic classification. And that's what we decided to try. And so symbolic classification is based on using a symbolic regressor and then a transformer. And the idea is to find a function that from an input of fetchers and fetchers can derive a number, a real number, and the transformer can go to a label which classifies, and here we work with binary class, for example, 0 and 1. We get a pair, a set of pairs of samples and their labels, a set of operators that will be used to discover the function, and a threshold that will help to stop the algorithm. And so this symbolic regressor is based on a genetic algorithm that will build a function out of the operators, and the fitness of every candidate will be assessed by a loss that in our case is the log loss fitness function. The stopping condition will be if the fitness is inferior to epsilon, and if not, then there is a mutation done by the genetic algorithm until the stopping condition is reached. And so we get in this in the way the tree is built, we have two faults at a node, two sets of faults at a node, the faults I samples, and we want to contrast with the faults G and the nominal data on the other hand, because we want to get a function that is sensitive to the fault I, but not sensitive to all the samples that are in the other set. And by injecting the knowledge of what the relation should be, the transformer function that classifies is taken rectangular, this means that when the function is close to 0, then we go to class 0, and when the function is different from 0, we go to class 1. So that's the injection of what we call injection of meta knowledge in the diagnosis tree. And by doing so at every node, we get a set of relations, and these relations we will see on the example here of the little polybox. These relations are, when we build the tree with the single fold samples, the relations, we find two relations that are exactly the ones that we would have found from the model of the polybox. So the third relation is missing here, but actually this relation is not useful to separate single folds. And when we run the diagnosis tree with the double fold samples, then we discover the third relation here, and we have all the relations that we would have found if we had a model of the system. So the properties of this kind of tree, we are now exploring them. I believe that this kind of tree is explainable by design, explainable in the sense of Joao, but we still have to prove this. And so it's a nice piece of work that Louis will continue. He still has some time to do this. The results, when he compared with respect to univariate trees, are here. The accuracy is much better, and we get these formal expressions of the relations that are known as analytical redundancy relations in the model-based diagnosis community. So more adventures in INITI2, I hope. I cross fingers. This I want to mention are pictures that are all taken during scientific events. Thank you very much.
Thank you, Louise. Questions? Joao. He wants to have the tree. Yes. Send. Email.
Oh, yes, I will. But this one is too small. We can send you another one, because right now we are working on dynamic systems, of course, which is a little bit more complex, because the relations that we are looking for now, they involve derivatives. And also Louis is testing the method on the 3D printer that is actually the main application of his thesis, and it's the application provided by Atos. So we can send you a few trees.
So I saw that you were using a genetic algorithm, and when you have much more nodes in your tree, you see the limits of this approach because of the exploration dimension that you have in the genetic algorithm. You have an idea of the scalability of this?
Actually, the genetic algorithm is only used at every node. It is not, so at every node, the data that is managed is the data to separate one fault from the rest, actually. Yeah, there is some, I didn't get into all the details, but the dimension is much smaller than the whole You mean as samples, the number of samples of each fault? We don't need so much, but Louis has the numbers. Yeah, in the experiment here, we have, no, this is only the results are obtained with generating 10,000 testing samples and 22,000 training samples, but you didn't put the number of faulty and not faulty. Yeah, okay.
Thank you very much, Louise.